go back into the past. Or even if they don't develop a singularity, you have questions of tunneling and quantum aspects of gravity that we need to understand how to deal with. And we really don't understand the theory, but we should recognize, we don't understand what the answers to these questions are, but these are really the most interesting questions in quantum gravity. They're more interesting than the questions about black holes that we are also studying a lot. And the reason we study these questions about black holes is that black holes are a simpler problem. And they are simpler because you can go far away from the black hole where the universe is not expanding, and it's very big, so you can set up very complex experiments and you can ask questions. And so for this reason, you can ask questions like the black hole information paradox and so on. And the idea is that by learning how black holes work, we might learn about the cosmological singularity, perhaps. And one important property of black holes is that in the interior of black holes, the interior of black holes looks a bit like a cosmology, a big crunch cosmology with a singularity. It's not isotropic, it's anisotropic. Some directions are expanding more than, or are not contracting at the same rate as others. But nevertheless, it shares with the primordial singularity the feature that it is also a singularity which occurs at some point in time. And we hope that our studies of black holes will teach us about the singularity. This hasn't happened yet. So we understand a lot about black holes as seen from the outside. We don't understand similarly well the interior of black holes. Okay, so that's so the roadmap would be to study the black holes from the outside, then the inside, then go to the singularity and understand then cosmology. Okay, so now people thought about both black holes and cosmology from the semi-classical gravity. And there is one interesting idea that I would like to describe, and I'd like to describe how it might be connected to the SCFT, and one problem with this idea, which is the Hartle-Hawking wave function of the universe. So before I discuss that, let me describe a little bit the concept of the wave function of the universe. Of course, in any quantum theory, we are interested in the wave function. When we have a quantum field theory, we have a wave functional, which is a function of the fields at some moment in time. And in gravity, we expect, therefore, some kind of wave function, which is a function of the fields at some moment in time, and those fields are just the 3 geometry on a particular slice, right? So if you are very naive, you say, well, those are the fields. In addition, you might think you also have fields which correspond to the G00 and GTI, right? So those components of the metric. And indeed, there are some other fields, but when you think about quantizing, the integral over those other fields act like constraints on this wave function. So they obey so-called reparametrization constraints and momentum constraints. So this wave function obeys some differential equations. One of them indicates that the wave function does not depend on the coordinates you choose for describing this 3 geometry. That's the reparametrization constraint. And the other is that it does not depend on, if you were considering 2 different 3 geometries that are related by bulk time evolution, also the wave function should give you the same answer. That's the Hamiltonian constraint. So if we had additional fields, so the idea is that we are computing a wave function of some 3 geometry. So this is some sigma 3. We might have also fields on living on this geometry. In that case, we will also have that the wave function depends on those fields. But this x is x in 3 dimensions. Okay, very good. So that's the object we are interested in studying. We can study it in semi-classical gravity. And when we think about it in semi-classical gravity, the leading approximation to the wave function is to say that this wave functional is I times the classical action of the classical solution. So when we think about semi-classical gravity, we start with a background space-time. So we might have some background space-time, and which is some classical solution, and then we have fields moving on that background space-time. And so in semi-classical gravity, the leading order answer would be you have some 3 geometry, you find the full classical solution, you evaluate the classical action. Okay? And then you can consider also quantum corrections and so on, which are additional factors that you get here. Now, so this is more or less standard. It works for any case. And now we come to the Hartle-Hawking case, the Hartle-Hawking proposal. And this is a proposal for the wave function in this de Sitter context. And what they proposed was the following. So imagine that you have some 3 geometry in the future. Then the idea is that you have to find, so you evolve backwards in time, and then into the complex space. So you find some complex solution. I will give some examples in a second. But this complex solution should be such that this manifold shrinks smoothly in the past. By past, we mean you might have to go into the complex direction. And then you evaluate the classical action. So let's see how this works in, just to be more clear, let's see how this works in a specific example. So imagine that we are thinking about pure, just simply de Sitter space, which would have a metric d tau square plus cos square tau d omega 3. This is just the metric of ds4. Okay, so there is a time direction. There is a three-dimensional space, which is just a sphere with some radius, which we'll think of it as our a of time in the classical solution. Now, in this wave function approximation, the idea is that we will find some wave function, which is a function of the 3 geometry. So the 3 geometry here will be a sphere of some radius a. And so this will be just a function of a. So we are ignoring the fluctuations of the sphere. We will include them in a second in our discussion. So it's a function of just one variable, psi of a. OK, that's what we are interested in computing. And in this case, this sort of complex solution is actually real. And it's composed of 2 pieces. So let me draw it here. So we have some S3 with some radius a. Then we evolve backwards in Lorentzian time up to the point where a is equal to 1, right? And at that point, we join the solution to the solution of in Euclidean space, which is, so this is a portion of ds4. Notice that with this time, ds4 just shrink, and if we continue to negative times, it will start expanding again, right? So the space shrinks and expands, okay, as we go forwards in time. So we have this. Now we can think of, in terms of the complex tau plane, what we are doing is the following. So we have the imaginary direction, and we have the real direction here. This is real tau. And so we find the tau. So we look at the solution. We find the tau where a is the value at which we are evaluating the wave function. Then we're going back in Lorentzian time up to tau equal to 0. And then we're moving into Euclidean time up to, so here in this region, we are setting tau equal to I theta, okay? And then the metric in that region, just by putting I theta here, we have ds squared equal now to plus d theta squared plus cosine square of theta d omega 3. Right? And this is just simply the metric of S4, okay? But we go up to minus I pi over 2, from 0 to minus I pi over 2, and that's just half of S4, okay? So this is half of the metric of S4. And then the proposal is that we evaluate psi, well, this psi of A. So you can evaluate it simply by inserting this metric into the Einstein action. This is a straightforward exercise that I will not do explicitly. But what we will get is we will get some pieces which behave like e to the I a cubed plus some other terms that go like a for large A. And these contain an I. So remember, we are evaluating the action I times I classical. So to the extent that we have a real solution, we'll get a pure phase for the wave function. This is, of course, as we usually get when we apply the WKB approximation or the semi-classical approximation with a real solution. But then we have the evolution here in Euclidean time, and that will give a piece that is, so it will be minus half the action. So if we had the action on S4, it's just half of that action, okay? Okay. Now it turns out that then that would imply that the square of the wave function is equal to e to the minus I, the action on S4. And this action on S4 turns out to be exactly equal to e to the entropy of the sitter, S of the sitter. So where S is not the action is I, S is the entropy. Now what is this entropy? So if we, it's the area of the cosmological horizon. So if we have, we think about the sitter. So this is the Penrose diagram of the sitter. This spatial cross-section here is S3. This would be the north pole of the S3. On each point on this diagram, there is an S2, which shrinks to 0 at this point, and it shrinks to 0 at that point. And so this is the north pole, and this is the south pole. If you are an observer that sits here in the north pole, you will only receive signals from this part of the space-time, this part here, right? And also, you will also be able to send signals only to this portion of the space. The intersection of these two is what's called the static patch. And it has the feature that we can choose some other set of coordinates that make manifest a particular isometry, some particular isometry of the sitter, which acts like time translations here. But in any case, so there is this horizon, and the area of this horizon is, so this entropy S the sitter is the area of this cosmological horizon divided by 4G Newton. Okay. And we can understand that that's what the action of S4 should be by thinking about this isometry and then going from Lorentzian time to Euclidean time, where this isometry becomes one of the symmetries of S4, and then just that action by the usual Gibbons-Hawking action. Well, it's similar to the Gibbons-Hawking calculation of black hole entropy. We will get that it should be proportional to the area of the horizon. Okay, so that's the answer we get. So now, very good. So this is all the standard discussion in the sitter. Now, this we will see later that this proposal has a phenomenological problem. So it seems to disagree with experiments in our own real world, and we'll discuss those problems there. But before we get into those problems, let's compare this with the ADS case, right? We are supposed to be learning some lessons from ADS. Now, does this concept of the wave function appear in the ADS case? And so the closest analog to this discussion is to think about the ADS problem as follows. So instead of considering the usual Lorentzian ADS, we consider the Euclidean ADS problem, okay? So we are going to consider a Euclidean situation. And in that case, what we normally say is that, well, we put some metric on the boundary, let's say some three-dimensional metric, and then we fill in this metric with a non-singular solution so in this case, it's typically a real solution. And and we evaluate, then we say that there is some gravity partition function that is given by summing over all this, and we approximate this by e to the minus the classical action, and we equate this to the conformal field theory partition function, okay? Very well. And in this case, in the simplest case where this surface is just an S3, in that case, we get a space, which is just simply our friend ADS4, Euclidean ADS4, or also called hyperbolic space. ADS4 or H4, okay? Now, we can similarly, so notice that at this level, the calculation, the prescription is identical to what we do, but to the Hartle-Hawking prescription in ADS. It's amusing that in their paper they said that their prescription does not work for ADS, but actually we are claiming it actually works very nicely. And we can evaluate the Euclidean action. So the Euclidean action will be like the volume of the S3. There will be volume of S3, and then some integral between 0 and infinity, the rho sinh cubed of rho, okay? Now this is infinite, so we normally put some cutoff here, and then it turns out that this integral will contain pieces that go like e to the 3 rho cutoff, so this is similar to the a cubed term that we had before, some piece, I'm not writing the numerical coefficients, e to the rho cutoff, that's the piece going like a in the discussion over there. And then there is something finite. Now, in this case, we say that these diversion terms can be viewed as local counter terms in the action of the conformal field theory, where in this conformal field theory action, we might have some divergences, which are of the form 1 over epsilon cubed, integral the square root of g, and then some terms that goes like 1 over epsilon integral square root of gr, right? So these are these two terms. And then we have some C renormalized, which is finite, right? So this computation is saying that this renormalizable partition function, renormalized partition function, contains this finite piece, okay? And what is this finite piece? It turns out that this finite piece, I'll explain that later, is actually essentially the same number that we had here, up to a minus sign. So it's some finite number. We'll explain that minus sign in a second. But what I want to emphasize is that in this particular case, if you are given a specific quantum field theory, for example, the ABJM theory, that's a three-dimensional theory that has a known ADS4 dual, you can actually calculate this from the field theory point of view. So in the field theory, you can calculate this number, and this was calculated, and then it matches with this gravity computation. So in this Euclidean setting, this prescription, the analog of the Hartle-Hawking prescription, works perfectly. So there are pretty detailed matches, not only of the classical action, but also the quantum corrections and so on, and for many different field theories. Okay. So what is the lesson of all of this? So the lesson, well, one lesson is that in this Euclidean context, the analog Hartle-Hawking works. And so it tells us that, well, maybe in the Lorentzian context, we should take it seriously, okay? We should take the Hartle-Hawking prescription seriously. Now, what exactly is it that we are doing this? We are doing in this particular case. So let's reinterpret here this C gravity a little more. So yes, please.
So somehow in the de Sitter case, we were calling it the wave function.
Yeah.
And now we are calling it the partition function.
Yes.
Could you comment on?
Yeah, I was about to mention that. Yeah. So here we normally call it the partition function, but we could also call it some kind of wave function. But a wave function evaluated on this big geometry, so we would evaluate it in the same way. is similar to the type of wave functions you get behind the barrier. So, and to be a little more precise, this wave function has the form e to the a cubed, so with a plus sign, well, here plus or minus a. So when we look at the ADS problem, we are picking up, by just looking at what we normally do, we are picking up the piece that grows, okay? And that piece has, let's say, C renormalized, so the gravity piece. So this is something we do in gravity. We have a piece that diverges, that becomes very large. This is this calculation. And then a piece that is finite, which would come from here, and plus perhaps quantum corrections. And this is what we normally call the renormalized gravity partition function. But it's just a coefficient in this wave function. So from here, I would conclude that we are looking at just one branch of the wave function, this growing branch. And that this wave function is unique, so because we get a unique answer. And so it's consistent with the philosophy of Hartle and Hawking that there is a unique wave function for the universe that we pick out using the Hartle-Hawking prescription. Okay. Now we will go back. We will go back to the de Sitter case and continue exploring this Hartle-Hawking wave function. And go to the question of what happens if we include small fluctuations. So,
Juan, I
yes,
just follow up. So usually when we compute the partition function, we integrate over all space, right? And here
yes.
we have put this row cutoff. Is that analog of like choosing a state somehow? Because it
so we're evaluating. Yeah, good. So we are evaluating the wave function as a function of a three-dimensional metric, and the overall scale of the three-dimensional metric matters. So that's analogous to putting a field theory with a cutoff.
I see.
So the idea is that the wave function evaluated on a very big manifold is the same as a CFT, some field theory with a cutoff.
Yeah.
And then we take the cutoff to infinity.
I see.
I mean, the size to infinity, that's the same as taking the length scale of the cutoff to 0. And, well, there are some things I'm not saying here, but there is a correspondence between the renormalization group flow and this Hamiltonian constraint and so on.
Okay, got it.
So the fact that as we change, so there is something important that happens is that as we change A, as we go to the future, this piece changes, but these changes are all local. They can be represented in this way. So this type of structure is a solution of this Hamiltonian constraint, where all these pieces that grow with A, that depend on A explicitly, are all local expressions. And then this could be a non-local expression, more complicated function, which is not just the exponential of some integral. And that piece that essentially does not depend on A. Yeah. And that's the conformal. So this is a function of G, and this function of G, so C renormalized is equal to C renormalized times arbitrary function of X times G, right? This particular case of the conformal field theory, that's just essentially the conformal invariance. Now, sometimes there is here some particular function, the conformal anomaly and so on, but that's a small detail. But the philosophy, I mean, that conformal anomaly is, again, a local function. Okay, so that's, yeah, so all this has been well explored. And we have a similar story in de Sitter. Again, in de Sitter, because those pieces that depend on A are just pure phases, right? And this is just saying that, well, the probability of having some universe doesn't depend on when I look at the universe, where I look at later times or earlier times. Okay. Okay, so now let's look at the problem of small fluctuations. So again, this picture here. So we imagine we have a big S3, and we have some small fluctuations. Now, does this prescription reproduce the or give something reasonable for these small fluctuations? Okay. So in this case, just this same prescription that we were discussing gives something very reasonable. I'll perhaps review it in a second. Let me just first state the answer. So we will get the answer we had before of, the zeta entropy divided by 2. So this comes from the global piece. But then there is a piece that comes from small fluctuations. Let me call gamma the small fluctuations. And the metric is delta ij plus gamma ij. So locally near each point, the metric is approximately flat and with some small deformations, okay? Times some overall factor, a function of time, which is expanding. So the point is that here we get something which is a Gaussian wave function with a minus sign, real, okay? So something reasonable for the fluctuations, so that they are telling us that having large fluctuations is suppressed. So we prefer to have smaller fluctuations. Okay, so one point is that this way of computing it, I'll go into a little more details in a second, but this way of computing it agrees with the standard way that fluctuations are computed in ordinary de Sitter space. So we have the Sitter space, there is there are various ways of computing the fluctuations, and this method agrees with the standard method. So this can be viewed as evidence for also the correctness of the Hartle-Hawking prescription for at least small fluctuations. Let me go into slightly more details about this. Ordinarily, so I said the metric can be written in this way. Dxi, dxj, delta ij plus gamma ij, right? And when you compute these fluctuations, so you can find classical solutions for gamma. And maybe I can also write this metric as minus d eta squared plus, dx squared 1 plus gamma, let's say, schematically, over eta squared. This is just the choice of conformal time. And the solutions of the classical equations around the empty de Sitter are particularly simple, and they have the form e to the I k eta. One, just in complete detail, you can solve them exactly and have this form, times some constant function. So this is the time dependence. So here, time going to infinity, so eta, so minus eta is like e to the time, right? So if this is the infinite future, we have negative etas, and eta equal to 0 corresponds to the infinite future. And at the infinite future, this goes to a constant. So we have a space-time with a constant fluctuations, constant in time. Now, so we have the eta direction. So this is so we have the eta line. So we have eta equal to 0, and we're interested in negative values of eta. So these are the Lorentzian solutions. And there is a second Lorentzian solution, which is just the complex conjugate of this, which has the opposite sign. Okay. Now, when we pick how we go into Euclidean time, this is like deforming this eta contour in some imaginary direction, which is similar to choosing the I epsilon prescription that we do in quantum field theory, that we evolve in time into Euclidean time, so as to select a vacuum, okay? And in this context, if we were doing just a vacuum, so we wouldn't have this term. So even if we were computing the wave functional of a field in Minkowski space, we would have a similar solution for a massless field, and we wouldn't have this term, okay? And in that case, we deform eta in a direction, so we deform eta in some direction, and we pick out of the two solutions the one that is exponentially decreasing, right? After we make the deformation, right? So let's say we make the deformation into negative imaginary time. So then here, I guess we would pick the one with the opposite sign than the one that I've chosen before. Okay, so the way we deform is chosen a priori. Here we choose the one that decays. Now notice that. Okay, and this is what we do in these flat coordinates, but this whole thing can be generalized to these curved coordinates. And in that case, we get some complex solution. It's complex because when we make this deformation, we get some complex metric. But it's a metric that asymptotes here, well, in this, when we do it this way, it asymptotes these fluctuations decay, right? And they go back to the zeta metric, and then we can do the continuation to the sphere. Very good. So that's that. Now, this should be compared to what we normally do in Euclidean ADS. So let's keep here Euclidean ADS. So in a similar situation, we would have a metric which would be dc squared plus dx squared over c squared. And again, we could be considering fluctuations 1 plus gamma here. I'm putting this schematically. And again, we would demand that the solution we would pick would be a gamma, which will be e to the minus k c, where k, okay, I guess I didn't say it, but I should have said it. K here is the modulus of the vector k that corresponds to a given Fourier mode in space. Yeah, I should probably have said that. So we take a particular Fourier mode in space, and then k here is just the absolute value of that vector. Okay. Okay, and here we get exactly the same story: 1 plus kc. Okay. And we pick the solution that for large c decays. Very good. Now, the two cases are very similar, but not only are they very similar, but they are mathematically related. So there is a mathematical trick that actually relates the answers for these two problems. So they are, I would say, almost identical. And mathematical trick is to notice that you could put c equal to I eta. And here the choice of sign I is chosen so that the things we are saying make sense. And then under this change, we see that the ADS computation, this ADS metric, becomes minus the eta squared plus dx squared over eta squared, right? And even if we have the plus gamma, we would also have it here. So the metric in the ADS case under this analytic continuation becomes minus the metric of the DS problem. So that means that the action of the ADS problem, so that means that if we are interested in the, let's say, the zeta problem, okay. So let's say we're interested, the problem we really care about is the zeta problem. Then that action ends up being the same as the action in the ADS problem for minus the metric. So this is a funny thing where in the action we put a metric with the overall sign, so an overall different sign in the metric. Now, how does that affect the action? So if we have the Einstein term, so for example, square root of GR, this Einstein term, so here, when we put this minus G here, there is an overall minus sign from here and two minus signs from here. So in the end, there is an overall minus sign. So this is minus the ADS, the action for the ADS problem for the metric G, okay? So what I'm saying here is that there is this, it's not just that it's very similar, but it's almost mathematically identical in the sense that if you solve one problem then you can put it back in the action, you get the same type of solution. In particular, so for example, we saw that the de Sitter action had e to the plus s de Sitter over 2. For the ADS answer, the finite piece of that partition function which we were discussing would be minus the corresponding s de Sitter over 2. So we'll have a minus sign compared to the previous one. Okay. Now, given the closeness of these two things, well, one is very tempted to think that perhaps this wave function that we've been writing here has, so that this wave function could be computed by a dual field theory as the partition function of some CFT, some kind of CFT, okay? Now, the discussion we had there implies that when we compute everything in gravity, whatever this is, it will obey all the word identities and properties that we expect for a CFT, okay? Because we did some continuations, it's not guaranteed that the CFT will have, let's say, positive anomalous dimensions, and in general, it will not have. It will have complex anomalous dimensions, for example, if you have a massive field. So some positivity conditions will not be obeyed for standard CFT. However, we might expect that we get some CFT. There is a particular positivity condition that is physically quite important that I would like to emphasize, just to see how those relations actually work. We said that a well-defined wave function of the universe for the small fluctuations gamma should have a minus gamma times some function gamma square. And if we want to be very precise about what this function is, it's minus integral d3k, so the gamma Fourier component k squared times k cubed, okay? So that's the explicit form of this exponent, and has an overall negative sign, okay? So that's the good de Sitter answer. There's a corresponding good ADS answer, which is the same thing, but with a plus sign. That's what we would get for de Sitter. And that plus sign implies, for example, that the two-point function of the stress tensor in the CFT is positive in the de Sitter case. So dt is, well, it's 1 over x times some positive x to the 6 times some positive number, c here, and c is positive. So that's for the ADS case. In the de Sitter, if we use the same definition of the stress tensor, that is to say the derivative of this with respect to the metric, then we would get a negative answer. So for the stress tensor, that tells us that this, whatever this is, will not be a reflection positive. So the positivity here comes from reflection positivity. And so this is not a reflection positive theory. So it's not a theory that can be analytically continued to Lorentzian signature if we analytically continue one of the field theory directions. Of course, this is not a problem because that's not what we are intending to do. We're intended, so in this CFT, whatever it is, it should give rise to a holographic direction that is time-like. And that's a non-trivial constraint on a CFT, and we don't really have very clear examples of CFTs that do this. So we have, well, maybe we could discuss what, well, yeah, so we, as opposed to the ADS case, we don't have an example of a dual pair where the left-hand side is some Einstein gravity theory and the right-hand side is some CFT. So the closest example we have is one example for higher spin gravity, where the left-hand side is some funny higher spin Vasiliev gravity, and the right-hand side is some non-unitary CFT of free fields. So, okay, very good. Now, there are, let's say, DSCFT skeptics. So let me now present an argument against DSCFT, and then a counter-argument. Okay. So the argument against is roughly the following. So here, when we were talking, So when we think about the zeta space, we assume that the metric in the future was just the metric of, let's say, flat space. But, well, the zeta will have fluctuations, and the typical metric will not be flat space, but will have some fluctuations. We've seen more or less how to include them. But worse than that, the zeta will decay. So there will be bubble nucleations that where we expect, especially in string theory, that the zeta is not stable and will decay. And the geometry will be some fractal geometry of this kind that will contain all these bubble nucleation events. So in some sense, the asymptotic structure that we assumed was not correct. Okay, it's not that it's not correct. It's just not the most typical thing. Okay, so that's the argument against. Now the counter argument. The idea is that if you assume that you have a smooth, so first of all, the geometry that you have here is some input when you decide how to evaluate the partition function here. You could put a uniform geometry, you could put a geometry that has a bunch of bubbles, you could put various things, and that the computation on the right-hand side should give you the probability of the various possibilities. If you choose a geometry which is just completely flat, then you are computing the probability that the zeta space does not decay, okay? And so it will have, that implies, so what would that give? So, well, that would give a wave function. And if we are saying that the zeta space cannot decay, then we'll have, there is, let's say, some decay rate of the zeta space, right? So this is the probability that it does decay. So the probability that it does not decay will go like the probability per unit volume that it decays times the volume of that the zeta space. So that's the probability that it has not decayed. Okay. And this volume, when we integrate up to certain cutoff epsilon, will go like 1 over epsilon squared, epsilon cubed. Okay. So it will look like, basically what I'm saying here is that this volume looks like looks similar to a counter term in the field theory. It's a counter term that now is real. Remember that before, when we were doing semi-classical gravity, all the counter terms, all the terms that look like this in the action had an I, but this would be a real one. So, okay, so it might be that this CFT, whatever it is computing the probability that the zeta does not decay, and we'll have some, if we really take the cutoff to 0, we have vanishing probability, but it's the correct answer. Okay. So it's not, the previous thing is not an argument against DSCFT. It is, if you wish, perhaps an argument about the relevance of a DSCFT or whether, but I don't view it as an argument against. Another argument, if you wish, against is just to look at this same calculation, these same observations that we were making here, but interpret this not as the glass half full, but as the glass half empty. You say, well, all the checks that you are doing here of DSCFT in terms of conformal field theory and so on just come from the fact that it's an analytic continuation from ADS. So it's not an independent check. Okay, so those were some general remarks about DSCFT. Of course, it would be wonderful to understand that better. There is another, before we continue, let me mention some other perspective on the zeta space, which is the static patch perspective. So far, we've taken what we could call the cosmological perspective, which is the idea that we are looking at observables that are defined here in the far future. These are observables that are not directly accessible to any particular observer in the zeta, but they might be accessible to some observer that if this the zeta then transitions into slow roll inflation and into sort of FRW evolution, radiation dominated or something like that, then they might be accessible to that observer. So we'll continue discussing that case in a second. But they certainly are not directly accessible to a particular observer. So a particular observer is, for example, this one that would follow this trajectory and has access to, basically can send robots and collect data from this region of the universe. Okay? And this region of the universe, so if you have this observer, let's say it's at the center, this observer looks like it is surrounded by this cosmological horizon, and you would be tempted by analogy with what happens with black holes to say that all observations, so to propose a different kind of correspondence, where you say that the observations of this observer can be described by, so this is the static patch holography, and it says that the static patch, all the observations that the person, an observer there, can make, can be described by some quantum mechanical system, in a system where the dimension of the Hilbert space is equal to e to the zeta entropy. Okay. So this is something similar to what you normally say about black holes. That you say if you have a black hole and you look at the black hole from, so if you are outside the black hole and you look at the black hole can be described by a quantum mechanical system with a Hilbert space which has dimension which is e to the area. Okay. So this is so here the idea is that the outside of the black hole is the same as the interior of this de Sitter space. Now, why is, so this is another idea that is also popular and is being explored for de Sitter holography. Now, why is it not identical to the black hole case? Well, in the black hole case, here we can go far away and do arbitrarily complex operations, right? Here, you are some observer that is in some sense some quantum fluctuation of this horizon or some fluctuation away from the maximally entropic state, which is just the vacuum. And you don't have access to arbitrarily complex observables. Okay, so that's a difference. So that's if you wish some argument against static patch holography. Okay.
Martin, there is a question in the chat that maybe has some relation here. Given the constraints on the CFT dual to the Sitter, could one geometrically engineer such CFTs?
Well, there are constraints that are simple, like the constraints of conformal invariance. But I think the main constraint that we don't know how to implement or how to find the CFT that obeys that constraint is that we want to find the CFT where the renormalization group flow has a holographic interpretation as being time-like as opposed to space-like. So we can define CFTs defining Euclidean signature. And the typical thing we think is that many of those CFTs, if they are reflection positive, they are likely to have a Euclidean ADS dual. But which CFTs have a time direction? And having that time direction is quite constraining because we want the evolution in that, let's say, RG time to be unitary. So that's a non-trivial constraint that the CFT should obey. So it's not some random, if you choose some random non-unitary CFT, it probably will not work. So it will only work for some of them. That's what I suspect. Okay, so now okay, are there any other questions? I'm going to leave the problem of DSCFT. So I think it's a very interesting open problem, and we would like to understand how to think about it. There are two perspectives. One is the cosmological perspective, where we look at observables similar to cosmological observables defined in the far future. That suggests some kind of DSCFT. There is some other perspective, which is the static patch perspective, which suggests the static patch holography. We don't know which of the two perspectives is correct. We don't even know how to relate one to the other. So is it true that, well, is it in some sense true that the DSCFT defined in terms of cosmological observables implies something like this or not? So it's the questions that you might have. Okay, so now I would like to...
It's a question.
Yeah, please.
Does there exist something analogous to SYK model for DS in low dimensions?
Yeah, that's a very good question. Not as far as I know. So yeah, there have been proposals, but I don't think there is any evidence that they describe de Sitter. So for example, Lenny Susskind had a proposal, but I don't think that there is evidence that describes the Sitter space, as opposed to some kind of ADS space. Okay, now I'd like to change gears slightly. So we've seen that this point of view where from the ADS answers we are gaining more confidence about the Hartle-Hawking proposal for the wave function of the universe. Now, also the recent progress in black hole information problem, the black hole information problem, the page curve and all that discussion, also gives us more confidence about semi-classical gravity and teaches us how to interpret semi-classical gravity. So this would make us more excited about the Hartle-Hawking wave function of the universe. So let me discuss first how the Hartle-Hawking wave function of the universe works for inflationary cosmology and a big problem that it has in that context, okay? So, quick reminder of inflationary cosmology. So the idea is that you have gravity plus a potential, right? So you have, and then you have some term in the action, so roughly like this, with a potential V, which has some roughly flat direction, and then it. So we are now here. The scalar field is at some very close to a minimum, and earlier during the expansion of the universe, the scalar field was roughly here, and in this region, the universe was expanding with almost constant Hubble rate. Okay, and the equations that govern the evolution there are it's almost expansion with constant Hubble rate. The Hubble this is just essentially the Friedmann equation, and where we neglect the kinetic term. And then there is some equation for the evolution of the scalar field, which is roughly like this. So derivative with respect to phi with the potential. So in the equation for the scalar field, we just pick just this friction term. We drop the kinetic term. So these are the two equations that govern the evolution here. That's just classical physics. And so the idea is that then if we have a situation like that, we have the universe today. It had some period of matter domination. We are now, or lambda domination. We are now matter domination, radiation domination. And then there is some place where there was reheating. And before that, there was the inflationary regime. Okay, so here we have an inflationary regime of almost the zeta revolution. So this is the regime in which the scalar field was in this region in field space. At this point, the scalar field comes down here and oscillates, transfers the energy to the radiation, and that's what we have in the future. Okay, so that's the picture in inflationary cosmology. Now let's say that the space in the future is some S3, perhaps with small fluctuations. And for the sake of this argument, yes?
This h square by something you have written? So this h square by something you have written which is proportional to v. This h square by something m square or something you have written. This h phi dot equation, that the above equation.
Yeah, if you wish, is h is just simply the Hubble expansion rate. So the dA d proper time over 1 over a.
Okay, no, the denominator.
The numerator, m
this.
Planck.
Okay.
So that's m Planck squared is 1 over g Newton.
That's fine. Okay.
Is that the question?
No, that's fine. Okay, thank you.
The V?
No, it's fine. The potential.
Yeah, V is the potential, V of phi.
Yes. Okay, thank you.
Is that that's answer your question? No?
Yes.
Oh, that I have the equation wrong. Yes. Yeah, you are correct. Yeah. M Planck to the 4th. Yeah.
Okay.
That's correct. Yes, yes. Sorry. Yeah, this is dimensionless. This should be dimensionless too. Thank you. Okay, so very good. Thanks for the correction. Now imagine that we have some S3 with small fluctuations. And for the sake of the argument, let's say that the whole observable universe is much less than the size of the S3. We're considering a very big S3. Okay, we could have a very tiny curvature. Normally, we parameterize the curvature in terms of some number k, which if it was 1, it would be the overall size of the universe, and if it is much more than 1, let's say 10 to the minus 5, it will be, well, very big and comparable to the size of the, so the curvature that we see of this S3 would be comparable to the curvatures we see from the small fluctuations. Okay, so we have that very big S3. So then when we evolve backwards into the past, let's say the scales of the observable universe, so something that is important for this discussion is when various scales cross the horizon. So when the physical size becomes of the order of h during the evolution. So the overall size of the S3 will become of order Hubble size at some particular value of phi star. Let me call it phi star. So this is the value of, let's say, phi star is when the big S3 that we have now becomes of the order Hubble size during inflation. Okay. If this S3 was bigger, the bigger we take it, the further back this phi star will go. Okay. So for a given potential and so on, as we make the S3 bigger, we start pushing back this value of phi star. Now, this whole part of the evolution is Lorentzian, so we'll contribute with an purely imaginary part in the action. So, but the wave function of the universe will contain a piece. The probability of having this universe will contain a piece coming from this Euclidean evolution. Oh, perhaps I didn't. I should. So we evolve backwards in time up to this point, and here, if we had perfect de Sitter, we can just join it to half of S4. Okay. This is not perfect de Sitter. There is a varying scalar, but we can modify the scalar a little bit so that it is smooth on the S4. Okay. And the value of the scalar in this region will be of order this phi star that we were talking about before. So this is a small modification of the evolution, but with this small modification, we can find this type of solution as we are instructed to find in the Hartle-Hawking proposal. So this is what the Hartle-Hawking proposal will look for an inflationary universe. And as I mentioned, if we do this proposal and we consider small fluctuations, and small fluctuations come out with the right wave functions. Well, or the wave functions that is reproduced by some other method. So the new aspect is we are able to calculate something about the probability of having a big S3. And then we find that this is the same as the de Sitter entropy, and this will give us m Plancks to the 4th over b of phi star. Okay, so that's the final answer. Okay, so here we approximated by the value we would have in the de Sitter space, where the potential is at phi star. Now, this answer depends on the size of the sphere. So it depends on, let's say, the radius of the sphere at the present time. And it depends through it because the bigger we make it, the further back we need to go here. And if we go further back, then the potential was higher. Okay? And that will be smaller. Okay? So this type of expression favors having a phi star, which is a v of phi star, which is as small as possible, so as to make this as big as possible. Okay? So it favors, so if you say that the universe at least has to have this size, which is what we observe, then it favors this S3 to be as small as possible to fit that universe. Okay? So it wants this phi star to be as close to here as possible. In fact, it even is better if we put phi star here, where v is much smaller. So where v, so that exponent there would be, so this exponent, so if it was today, it's 10 to the 120, okay? So it really favors an empty universe. So one way to say this is that it favors an empty universe, not the universe we observe. Now there, you could perhaps get, and it's hard to get around that with anthropic arguments, because it's easier to have an empty universe with a so-called Boltzmann brain, so something that has only all your memories. So it gives something that looks ridiculous. Okay. Now you might say, well, maybe I shouldn't. For some reason, I shouldn't put the v of phi today. So the way I like to phrase this argument is that maybe for today there might be some reason we could not put the v of phi today. There is, but I don't see any reason why we couldn't do this in the context of inflation, because we already are evaluating something analogous to the Hartle-Hawking wave function for the small fluctuations. this is just some bigger fluctuation of the overall, geometry of the universe, or bigger. So why couldn't we use almost the identical procedure to evaluate a question about the size of the universe? Let's say we put the constraint that it should be bigger than the observable universe, but it should be equal to the observable universe, twice bigger, and so on, right? Or much bigger. So from experiment, we know it's much bigger. And okay. So we can further estimate what's the kind of pressure that we have towards having a small universe within this context of inflation. Okay, so you can. This is again a simple calculation, so we can calculate again ADA of this 1 over V. Okay, so how it changes under rescaling of A, and you can use here. So this is B prime over V squared, and then ADA of phi star. So ADA is basically the number of e-folds. So this is like the derivative with respect to the number of e-folds during inflation. And so we get the derivative with respect to the number of e-folds of phi. And then this is the same as, so the d of the number of e-folds is h dt during inflation. And so this quantity here is 1 over h phi dot during inflation. Then we use the second equation to write it as 1 over h squared times b prime. And okay, so this whole thing then ends up being something like b prime over b squared. So b prime over b squared times 1 over h squared. Okay. And then we can put all the factors of M Planck. Now this is a quantity that is normally called, this is a quantity that is normally called epsilon in the discussion of inflation. It's a slow roll parameter, so when this is the condition that the potential is flat. This is supposed to be of order more or less 1%. And then this is M Planck squared over h squared. Now, when you calculate the amplitude of the small fluctuations here in this region, the amplitude of those small fluctuations, so delta, let's say, zeta, the curvature fluctuations, are the scalar curvature fluctuations are of the form 1 over epsilon M Planck squared over h squared. And you see that it's the same combination that appears here. So let me call this is, we know from experiment that, we know from experiment that the fluctuations are 10 to the minus 5, so this is 10 to the minus 5 squared, okay? So that means that if we just change this by a small delta n, we get a minus delta n, so a little bit more or less inflation, times a factor of roughly 10 to the 10, okay? So there is a huge preference to make delta n negative. That means there is a huge preference to making inflation shorter, okay? So it's not as bad as the 10 to the 120 that we had before, but still is pretty bad. Okay, so this I think is the, well, this is at least the simplest
question. So, but if inflation is shorter, all the observables that inflation washes away, will it still work? So
well, here inflation shorter means, well, it depends on what you want to say. So it has such a preference to make it smaller that, well, maybe there is no inflation. So that would be the conclusion you have from this. But if you put some input, like you should at least have a galaxy, okay, the size of the universe should be a galaxy, then you can start saying, well, maybe we need many galaxies because life is rare, and then you can have it in this way. You could try to get rid of, so there's one proposal for getting rid of this problem, which is this particular version of the problem, which is to say that maybe life is rare. And then, so we need a very big universe to get that probability higher. Or there was another related proposal, which is that when we make some observation, we need to input the value of the observation we want, and we want that observation to be likely in the whole universe. This is a weird, I think, point of view, but it's a point of view that Hartle-Hawking and Hertog proposed to get rid of this problem. But well, once we start thinking in this direction, we encounter the so-called measure problem, which is how we should assign probabilities in this context of inflation and so on. And it's a problem that has not been understood. It seems that we will need, well, in this proposal, we have to use the wave function of the universe and then input some, and then maybe add something else. Or I would expect that the Hartle-Hawking wave function should be enough to ask these questions about the measure, but of course it has these other problems. Okay, so one attempt to deal with this is just to ignore this and say, well, the wave function of the universe that Hartle-Hawking proposed is just wrong. We will not apply it. Instead, the picture of the early universe should be that of eternal inflation, followed by bubble nucleations of various universes. And that tends to produce universes with negative spatial curvature. But then again, you still have this measure problem that you don't know a priori how to calculate. And I would say that this second point of view is the one that is most popular among the people who think about inflation and the measure problem. But I think that just purely from a theoretical point of view, if you just are a theorist accustomed to, let's say, ADS-CFT or semi-classical gravity, I think the Hartle-Hawking proposal is the most natural one. But it has this problem. So we have a puzzle. So you could think of this as a kind of analog of the information puzzle. So some puzzle where applying semi-classical gravity strongly disagrees with our observations. So it's, I think it's an interesting problem. And I mean, the fact that we don't know how to solve it, well, that does not make it uninteresting. It's still interesting, but maybe it's an opportunity. Okay, any questions? That's all I plan to say about this problem. I think this is a problem that should be kept in our mind. We should understand this problem well, and if we encounter something that appears to give a solution to this problem, we should explore it.
Okay,
Yeah.
This is probably very, very naive, but so when you construct these pictures for Hartle-Hawking states,
yeah,
what is exactly the physical meaning of the Euclidean part at the beginning? Is it some sort of preparation of an initial state, or what?
Well, I mean, the idea, the philosophy here is that we are computing the probability of some observation now, right? And this whole history is some mechanism for computing those probabilities. We don't assign any particular reality to this process. Now, some people have tried to assign some, to interpret this as tunneling from some other space, so tunneling from a very tiny universe. If you take that point of view of tunneling from that, maybe at the very early stages you have a very tiny universe, and then you tunnel to some size A, you actually get the Hartle-Hawking wave function, but with the opposite sign. So you get, well, the factor here would be opposite. That's the so-called Vilenkin proposal. So Alex Vilenkin proposed this proposal. Now, in the ADS case, this sign is the correct sign. So the sign you're using here for the ADS case would be the correct sign. Now, maybe for the Lorentzian case, we should use a different proposal. So I mean, that's one of the ideas out there. Maybe I should say that a little more explicitly. So, well, this discussion. So if we look at just wave functions that depend only on A, right? Then this is a bit like a quantum mechanical problem where we have A, and we have some kind of effective. So we look at the full Einstein action, and we reduce it to metrics which depend only on A. Then we have a quantum mechanical problem for A, which looks like a particle in a potential. And the potential has basically the following shape. well, I now don't remember. I should have. Yeah, I think it has a shape like this. The important part is that here, and then we are looking at zero energy states. So this is the region where we get a wave function that oscillates, and that corresponds to the, well, if the wave function is incoming, that's the contracting phase of the de Sitter space, and then when it's outgoing, that's the expanding phase. And then here we get some exponentially suppressed wave function, which for the Hartle-Hawking state looks like it's exponentially growing in this direction, and then it starts oscillating. So that's the wave function that they chosen. Vilenkin instead says, well, if we were imagining that the computation we should be doing is to put the initial condition that you start at the universe at very small, then we should get a wave function which is somehow has some unit probability here, and the tunneling will give you an exponential suppression up when you get to this point. Okay, and that's roughly why the sign is opposite. Yes. Yeah. Here, this is the so-called mini superspace approximation of the Wheeler.
So what is Vilenkin solving?
Well, Vilenkin is also solving. The difference is which boundary conditions we're putting. So Vilenkin would say, well, here we don't know what happens at a equal to 0, but we use the same formulas, but with a different physical interpretation. Where here, again, there is something we don't know, and when we use a tunneling wave function to tunnel from small a to a of order 1. Okay. So, and that tunneling is suppressed as ordinary tunneling is suppressed.
Okay.
Yeah, that's his idea. But well, with the Vilenkin proposal, you have to say something now. Why was 0, and there is something here you don't know. In the other proposal, you are computing this using the Euclidean geometry, and there is nothing singular at 0. That's with the Hartle-Hawking proposal. Okay, so other questions about this? Okay, so now I will change gears completely. I didn't know how much time I would have for what I would like to say next. So we've seen various applications of ADS, of gravity and ADS-CFT to various problems. Maybe there is one potential set of connections. Well, there's some application which hasn't happened yet, but maybe it might happen. So, and this is the connection between artificial intelligence and holography. Okay. Now, of course, artificial intelligence is now everyone talks about it, so we have to put it in the talk. So I did ask ChatGPT what's the connection between artificial intelligence and holography, and it gave me a pretty reasonable answer. So it gave me something. So I'm not better than ChatGPT to explain this relationship. And you can try and find yourself what it tells you, and I think it's a reasonable answer. So I think, more precisely, I think there is some interesting set of ideas, which are the ideas of tensor networks. And holography. And this is what makes some connection to AI, where we have neural networks. But let me first discuss the connection between tensor networks and holography. So what are tensor networks? So tensor networks are originated as a computational technique to represent complex quantum states. So you have complex quantum state, let's say, so suppose the simplest case is you imagine you have a bunch of particles on a line. Let's say it's a closed line, a closed circle. And on each particle is a spin-and-a-half particle that has various values of the spin. So the wave function is some function with, so let's say there are L sides. It's a function which involves 2 to the L possible numbers, which are these amplitudes, okay? So each of these could be plus or minus. So there are 2 to the L parameters in the general wave function. So to specify a quantum state of the full system, you have to give 2 to the n parameters. Now, the idea of tensor networks is that, well, typically people say, well, the Hilbert space is very, very big. So when you have, let's say this is L, sorry. So it's huge, but the states of physical interest that are, let's say, the low energy states of some Hamiltonian or that arise in physical computations typically form a small part of the big Hilbert space. They're in a small subset of the whole Hilbert space. And the idea is to try to parameterize that subset appropriately. And in this case, a parametrization that has been particularly useful is to think of this as, instead of giving those numbers, we give the state of a bunch of matrices. So we pick a bunch of matrices. So we have, let's say, D times D matrices times 2. So for each values plus and minus, we have a D times D matrix. The matrix could be all different. If they're all different, then there is an additional factor of L. But the idea is that when L goes to infinity, this number, which is the number of points we want, is much bigger than this number. Okay. If we keep D fixed. Okay. So if we keep D fixed and make L large, this is a small subset of the whole Hilbert space. This is called the matrix product state. And ground states of some Hamiltonians, they typically have this representation, where D is not too large. Now, what is D related to? So suppose you take that chain that we were discussing, and you cut it in half. Okay. Yeah, perhaps it's useful to introduce a graphical notation for this operation, which is this. So here, each vertex represents a T, and this line represents the spin, and these lines here represent the indices of this matrix. So TS, some matrix of indices I and J, where I and J go from 1 to D. Okay. Now, the states that can be written this way have a special property. And that special property is that if you look at the von Neumann entropy or the entanglement entropy of a subset of these spins, so let's say at these 4 spins, then that entanglement entropy is bounded by twice the logarithm of S. Okay. So this type of discussion works well for states where they are not very long-range entangled. So there is some maximum entanglement. So the entanglement between big portions of the system and the rest, or any portion of the system and the rest, is bounded by, so S entanglement is less or equal than twice log of D. Okay. So for states that have this bounded entanglement, then it will work well, and many systems have this property. So the advantage of tensor networks is that they make these entanglement properties manifest. Of course, if you change the entanglement properties of the system, then you might need to change the network. So this works pretty nicely for gapped systems. If you have a gapless system, then there is another network that works a little better. I'm going to draw it like this. So each line is, each vertex is a tensor with as many indices as the lines that come out of it. And so on. So you have, you can make something roughly of this structure. And so this is a feature, this is, with this structure of tensors now, if you have, if you're looking at some small set of spins, then there is, let's say, high entanglement between these 2 spins. But if you start looking at regions that are distant, there is a little less entanglement because it's mediated by a smaller number of lines. Let me be, perhaps there is a connection. Well, I'm going maybe a little fast here. Here we can calculate the entanglement entropy roughly by, a bound on the entanglement entropy by cutting these lines, right? And assuming that this index is somehow maximally entangled. Then that's what gives us the 2 log D. We can do a similar story here in this more complex network. And let's say if we look at all these spins, then we would like to cut all these lines. So we have an option which is to cut all these lines, or we could cut, if we go deeper down, then we could cut a smaller set of lines and so on, right? And so we can move the surface to see, try to minimize how many of these lines we cut. And then we will get an answer for the entropy that looks somewhat similar to what we get from the Rutakanagi prescription, that we take some surface and then we move it around to minimize the number of lines that we are cutting, minimize the area. So you can think of the area as the number of lines that you are cutting. So if you think that these tensors are completely random or that they're very complicated, then that will give an accurate representation for the entanglement entropy. And so then these networks are making geometric the structure of entanglement, okay, somewhat. And we expect that space-time also has this property, that space-time is making geometric some aspects of patterns of entanglement, because the Rutakanagi formula is telling us that the entropy is given in terms of the geometry of space and the geometry of a minimal surface, or something very basic about the geometry of space. So these tensor networks are embodying that and are nice. Normally I discuss at toy models. Yeah. Go ahead.
Is this somehow connected to bit threads? There's also a way to calculate entropies in this way.
Yeah, in principle, well, yes and no, in the sense that bit threads and this gives the same answer. I don't know if you can take a tensor network and define the bit threads already there. Perhaps you could. There might be some equivalent way of thinking about it, but I don't know of a precise relationship between the tensor networks and the bit threads, though it might be in the literature. Okay. Let me see. Now, you can. There is an alternative way of thinking about this, which is also interesting, which is how think of generating the quantum state here, right, by a unitary evolution acting on a bunch of decoupled qubits. So we have a bunch of qubits, let's say all in the plus state, and then we start with 2 qubits. So we add extra legs so that all these deformations that we have here are all unitary. And then we can add extra legs where we supply qubits in, let's say, the 0 state. And then this whole operation becomes a kind of unitary circuit that prepares a complex wave function out of simple building blocks. Okay, so you have a simple, so this to some big power k, let's say, and then out comes the wave function that we want. Okay, so it prepares a wave function in this way. And so we can think of the tensor network in that way as preparing something. So if we think about it in that way, we could also think of the Sitter space in this way. So the Sitter space, the evolution in the Sitter is similar in the sense that the Sitter space is expanding. There are modes that are in at very early stages, if you follow them from the future, have proper length scale, which is sub-Planckian, very tiny, right? So they start sub-Planckian, and then eventually they become of order Planckian, and then of order the Hubble size, and so on. And the crucial assumption that we normally make in dealing with inflation is that when they are sub-Planckian, they come in the vacuum. So they come in a simple state, and then the evolution sort of makes it a little more complicated, gives rise to the fluctuations, and encodes it in the wave function that we see, for example, in the probability distributions that we see in the primordial fluctuations in the CMB, for example. So this picture is generally enough that we could think of it as giving you the Sitter space or an ADS space and so on. And okay, what does the AI have to do with it? So think of an AI problem where you want to generate an image, right? So you would like to generate an image. Now, an image, if it's to be recognized for us by some as a reasonable image, it has to follow the same statistical distributions as the images we are usually presented with. So there is some probability distribution of images, and the AI has to generate such an image. And it does that with some randomness. So it doesn't always give you the same image. There are some random numbers that go in, right? And then there are some series of transformations which have also structures, well, not exactly this structure, but some structure of the so-called neural network, which consists of some series of transformations that we do of that. So we pick n separate, let's say, Gaussian variables, and then we apply a series of nonlinear transformations that will give us, will sculpt for us the probability distribution that we are interested in. So in that sense, I think there is some vague similarity between the two. I don't know if it can be turned into something useful or not, that we could say something that is useful for them, or that they can say something that is useful for us. And I would like to emphasize that in the past, connections between holography and more applied problems, let's say condensed matter physics problems, for example, they have been very, very useful. Not only for the condensed matter physicists, but also for us. So for example, there was a condensed matter physicist that was thinking about entanglement entropy, and Ryu, and he asked Takayanagi whether he knew some way of computing the entanglement entropy in gravity, and they came up with this prescription that we now call the RT formula. And the RT formula, in some sense, was very useful for studying holography, was very useful for learning about condensed matter. Now we think it's very useful for understanding quantum gravity. So it has become very central in the study of quantum gravity, and it came from some application, if you wish. So there was this application and this question that arose there, and then it was recognized that it had this very bigger application and bigger range of it had a bigger importance. It's probably even more important than ADS-CFT. It's just comparable to the black hole entropy formula in its importance. Very good. And another example is the case of the SYK model, where you're using holography to understand strongly correlated materials, and then, well, okay, there is this strongly correlated system that looks like ADS2, and then now we learned new things about ADS2, for example, about near-extremal black holes and the quantum mechanics of near-extremal black holes that we understood thanks to the SYK model. So maybe, okay, if I was asked to make a proposal of an interesting field, maybe it's this field of AI, that there might be something that either they teach us or we teach them that might be useful. Okay, thank you. I will finish with that.
Questions, comments? Let me start with one. What do you have in mind there?
Well, I have in mind, I think I recommend the ChatGPT answer. I don't have any very concrete thing in mind, because, it's just that in both cases we are representing a complex complex state. So state in quantum mechanics, I mean, if you take the square of the wave function, that's a probability distribution. And we are representing that probability distribution in terms of simpler objects. So the tensors of the tensor networks, or the in that case, or in the AI, the neurons of the neural network. So in terms of simple building blocks, I think that's the simple analogy. Now, there are many other questions you can ask, so that I don't know the answers to. So in AI, it's important to train a neural network. What would that mean in terms of the tensor network? So given a probability distribution, find the space-time that reproduces this probability distribution, for example, would be that. Is there something we know about physics that could help us illuminate this or get some intuition about this process? Or, I feel these are some questions we might be interested in.
More questions or more comments? Thank you very much.